Hey there, class. Mr. Prusky here. Hope you're having a good day so far. Today we're doing 2.4 day 2, which is direct variation and linear models. So let's go ahead and get into it. So direct variation says two variables x and y show direct variation. Change my color here. Provided y equals k times x and k does not equal 0. The non-zero constant k is called the constant of variation. The constant of variation, and y is said to vary directly with x. Okay, so it says the example, the variables x and y vary directly and y equals 19.22 when x equals 6.2. Write an equation that relates the variables and then find y when x equals 8. So we're going to do that example in a little bit here, but first thing I want to do is I want to kind of talk about what variation, like direct variation, actually means. Okay, so the equation is it's going to be y equals k times x, or another way to write this to check if you're looking for what what k is going to equal. I could also, if I do y equals k times x, I could divide both sides by x to get k by itself. If I'm looking for what the actual constant of variation is actually going to be. So we can do y over x. Let me write it to the left over here. The other way to write it, these are going to cancel. We can also write this as k equals y over x. Okay, so these are the two different types of equations that we can use. There's probably other ones we could use as well, but those are the big ones. And so let's write down a couple notes here what this is going to say. So direct, and write this down nice and slow here. Variation, direct variation means if you scale or multiply x by an amount, y will also, also scale by the same amount. Okay? So let's do a couple examples here just to kind of figure out what this is going to be here. So, for example, if we have an x and y table, and we're doing the equation y equals 2x, right? So when x equals 1, 2 times 1 is going to be 2. When x equals 2, 2 times 2 is going to equal 4. When x equals 3, 2 times 3 is going to equal 6. Okay, so that's kind of the thing here. So basically, direct variation, the relationship between y and x is always going to be the same. So what does that look like? So we can use this y over x kind of thing right here. Okay, so this is a direct, if this data it directly varies with each other, or varies directly, we can take y and divide by x. So 2 divided by 1 is going to equal what? It's going to equal 2. What about 4 divided by 2? That's also going to equal 2. Yep. And what's 6 divided by 3? That's also going to equal 2. So if these vary directly, that means they're also going to, they're all going to divide y divided by x. They're all going to equal the same thing, which is 2. You can also think of it another way. The difference between, like when you scale x up a certain amount, y will also scale up the same amount. So if I do from 1 times 2 is 2, you can see that also 2 times 2 is going to be 4. Or 1 times 3 is times 3, and 2 times 3 is 6. Okay? So it varies based on, like, if you just change x a certain way, y will also change that same way. Or you can also, you can also do the same thing with, different y over x, that is, the y over x situation, where the relationship between x and y will be the same regardless of which point you're talking about on the data. What you call it? You get what I'm saying. Anyways, so that's kind of what we're talking about here, all right? The same thing applies to if you have like y equals 1/3 x, for example. That's kind of sloppy. Y equals 1/3 x. So if we do our x and y, so let's just start with let's just do 18. So 18 divided by 3 is going to be 6. If we do 9, 9 divided by 3 is going to be 3. And if we do 3, 3 divided by 3 is going to be 1. So same thing here. 6 divided by 18 equals 1/3, right? Same thing between 3 over 9 and 1 over 3. And also, if you do 6 from 18 to 3, that's times 1, 6. If you do the same thing here, this is times 1, 6. Okay? So it's the same kind of thing. So yeah, so that's kind of how that works. All right, so that's direct variation. So let's go into these actual problems now over here. I think that hopefully explains it well enough. But basically, what you multiply, whatever y is going to equal whatever you multiply the same number by x, it's going to change that same way. Okay? So let's get into this problem here. It says the variables vary directly, and y equals 19.22 and k equals 6.2. So we had y equals k times x is one possible one we could use, or we could do k equals y over x. Which one do you think would be easier to use if we're looking for what it says write an equation that relates to variables and find y when x equals 8. All right, if we're looking for what y when x equals 8, we'll do that first. Let's figure out the we need to figure out the equation here first of all. So let's use the top equation. So we're going to do y equals k times x. No, actually, we're going to use the bottom one. I'm sorry. This is a very sloppy video. I apologize, guys. We're going to use y equals this and x equals this. So we're going to actually use the bottom equation. So k equals 19.22 divided by 6.2. And k is going to equal, we're going to get 3.1. So our new equation, we need to figure out what the equation is going to be. We need to figure out what the constant of variation is going to be, how it's going to vary directly based on this data here. So it's going to be y equals 3.1x. And now that we know that, we can take this and we can plug it in and solve for, we're looking for y or when x equals 8. So I'm going to plug in y equals, we're going to do 3.1 times x, which is 8. So y is going to equal, it's going to be about, exactly actually, 24.8. Okay? So these are our two answers right here. We have the equation, y equals 3.1 times x, and y equals 24.8 when we plug that into the equation. Okay? So that's direct variation. So let's go ahead and get into an actual problem here now. Okay? It says, what does the data show direct variation? If so, write an equation relating x and y. All right. Well, so we need to figure out if it shows direct variation. So the quickest way to figure this out is to do k equals y over x. Let me write that a little bit farther to the left, actually. Okay, the quickest way to figure this out is figure out what the k is going to be, because they should all be the same between each of the different data points here. So let's figure this out. So we're going to do 4.5 over 3. We're going to do 7.5 over 5. 16.5 over 11, and 22.5 all over 15. And when we do that, they should all equal, this is 1.5, it should all be equal to 1.5 when you divide those nicely. So these are all the same. And so our equation, we're going to do y equals k times x. So this is our k value. This is our constant of variation. That's how the difference is between the y and the x. Okay? So our final answer is just going to be y equals, the equation is going to be our k, which is 1.5 times x. That's all you got to do. Okay? You just figure out the difference between y and x, because it needs to satisfy this equation, y equals k times x, and this is just a different version of that equation. And that should be your answer. Nice. All right, not too tricky, hopefully. All right, linear models. Okay, this is going to be good. So we have linear models as the independent variable and the dependent variable. Do you guys know which one's the independent variable? Was that x or was that y? Independent variable is something that happens no matter what. So that'd be like time. That'd be like, time is probably the biggest one, I think. Basically, you usually use time to describe or to measure another different variable. That's usually going to be our x value. We use x, the x-axis, to measure something. So basically, like, for example, you're measuring the temperature during the day. what time of day it is that will affect what kind of temperature you have, right? That means our dependent variable is going to be y. We're measuring y using x. All right, so let's go ahead and get into this here. It says in 1991 there were 57 million cars. It should be cats actually. That's cats. Cats as pets. They don't keep cars as pets, I don't think. In the United States, by 1998 this number was 61 million. Write a linear model for the number of cats as pets. Use this model to predict the number of cats as pets in 2012. Okay, so what are we using to measure, what's our independent variable? What are we using to measure, are we measuring cats or are we measuring what year it is? We're measuring cats, right? So actually our independent variable is going to be years for this one. Okay, think about what you're trying to measure. And since 1991 we're actually going to talk about here in a second. Okay, so we're using years to measure how many cats. Okay, the number of cats there are in the United States doesn't impact what year it does. That would be kind of silly, wouldn't it? Okay, and one thing I'd be careful about with these kind of problems is we're not going to use 1991 as a data point. We're actually going to use the first year. That's going to be our 0. That's going to be our y-intercept. And so that's why I put since 1991. Okay, and the reason for that is that if you use 1991 as an actual like ordered pair, that's going to mess up your data quite a bit. Whereas we're just talking about these years are going to be in reference to 1991, how far they are away from 1991. Okay, so our first year that we're using to measure, that's going to be our 0. That's going to be our y-intercept. Okay, so what we're going to do, let me see here. All right, so we need to figure out, so how many cats were there in 1991? Well, there were 57. That's going to be our y. And I'm going to use 0. 1991 is year 0. That's where we started. Okay? Now, in 1998, we had 61 million, right? That's going to be our y. What was our x? How far is 1998 from 1991? That's going to be 7 years in the future, right? So we're going to put 7 for our, that's going to be 7 for our x for this coordinate here, for this ordered pair. Okay? So it says, use this model to predict the number of cats in 2012. So what we need to do now is we need to find the slope to be able to predict the future number of cats. Okay? Oh, one thing I forgot to mention, I used 57 and 61. This is kind of a trick. It was 57 million cats and 61 million cats. But if you keep the if you keep the units the same throughout, you can just call it 57 million. Just know that it's going to be 57 million and 61 million right here, okay? Instead of writing out, instead of writing out 57, using this as an actual number that you're going to be measuring, just use 57 and 61. Makes it a little bit easier, okay? So now we have these ordered pairs. Now we can figure out the slope, which if you recall, it's y2 minus y1 over x2 minus x1. So we go x1, y1, x2, y2. Because we need to use the slope to figure out like where it's going to go in the future, right? It's going to be kind of to help us figure out how far up we're going per year, right? So we're going to do m equals, we got y2 minus y1, so we got 61 minus 57 over, then we got 7 minus 0, which equals 4. 61 minus 57 is 4 over 7. So that's our slope. So our new equation is going to be y equals 4/7 times x plus, what's our y-intercept? Well, y-intercept happens when x equals 0. What was our starting value for starting y value for this equation? It was what? It was 57 million, right? Cool. And now we're trying to predict, that's what we have so far, now we're trying to predict the number of cats as pets in 2012. Okay, well we got to figure out how far 2012 is from 1991. So I'm going to subtract these to figure out how far in the future that's going to be. That's going to be 21 years in the future from 1991. So we're going to take this 21, we're going to plug it in for x, because we're plugging that in for years since 1991. So we're going to do y equals 4/7 times 21 plus 57. And if you multiply that, you're going to get y is going to be equal to, it's 69, but be careful, it's not 69 cats, it's 69 million cats. Okay, 69 million cats. And that's going to be our answer. So a couple things to review for this, all right? your starting year is going to be your year 0. Your starting year is going to be your year 0. You're not going to start with 1991. It'll give you the right answer down here if you're putting it into the slope formula, but if you plug in 1991 into this, it's going to be really goofy. It's going to be a really big number. Well, let's just do that. So we plug in 4/7 times what? 2012 plus 57. You can see how that's going to be a huge number. There's not going to be that many millions of cats, right? That's why you have to make sure you give it like some scale. That's why we changed it to 21. We changed it to 21 because that's how many years it is from the starting point. It's not 2012 years in the future. It's just 21 years in the future, okay? All right, and then the last thing I guess to talk about is don't use if they're really big numbers, just use like the number in front of the big number, and then just kind of remember at the end you need to add that back. Okay? Otherwise, we should be good. Hopefully, direct variation makes sense. But thanks for watching. You guys have a great day, and we will see you soon.